In this video, we're going to take a step back to survey where we are in the class and reflect on all the amplifiers that we've seen thus far. Our overall goal this semester is to build an op-amp, so it's worth asking how our current work relates to that goal. We're currently working on an intermediate goal of building an interesting multi-stage amplifier, and we've already largely achieved that goal by learning about an assortment of single-stage amplifiers and coming up with rules to combine them into multi-stage amps. Getting there required us to cover some basic device physics. We started with diodes, then learned about BJTs, then our first amplifier, the common emitter, and that brought us to the present, where we're studying various single-stage amplifiers and the multi-stage amplifier model. As we've analyzed our collection of single-stage amplifiers, we noticed that we were doing the same math over and over again, which we started referring to as small signal patterns. I've tried to summarize some of this information on a few handouts you can find on the website. One of them is the handout for today, which contains a table summarizing the properties of single-stage amplifiers, and the other is a reminder of how to analyze small signal patterns. However, you don't need to wait for the handout to see a table summarizing what we know about single-stage amplifiers, because I've also included it here. Each cell contains a model for one amplifier parameter, and that model often contains a lab approximation, which is a simplification of the full model. The lab approximations are great design tools, but if you're trying to get an analysis exactly right or debug a discrepancy in your model, then you should use an exact model. Also, note that some of these approximations are more or less detailed than others. For instance, all of the entries that show RC in parallel with beta RO are actually combining a handful of approximations to get the beta RO impedance over on the right side of the parallel combination. But the beta RO is so much bigger than RC that I didn't think getting more detail over here would be worth it. Finally, note that the R in and R out entries for the common base are for the amplifier with a finite value of RO, which is different than what we derived in our common base video. So in summary, we're done with resistively loaded single-stage amplifiers. Resistively loaded single-stage amplifiers are important components of multi-stage amplifiers, which are in turn used to build op-amps. And to fill in the rest of our op-amps, we're moving on to other analog building blocks and tricks in the near future.